So feel free to jump in there if there are things things you want to go over. But first of all, first order of business is to welcome Dieter here. It's nice to have him here. And he'll be filling us in on some of the exciting work he's been doing, building up a multi-grid solver. So I'm really excited to see this. But before we jump in there, let's maybe just do, if there's quick updates from anyone. So UDC folks, is there anybody who's got a quick update or thing that they want to share?
I guess, yeah, I'm starting. So I've been working on tutorials. There's been a few people that want a bit more of a detailed explanation how to create meshes, usually tree meshes and sill meshes. So yeah, I've started a set of tutorials on the Discretize website, and I'm planning to do some on SimPEG as well. Lindsay and I guess Bain have offered review, so the sort of first set of tutorials should be merged into the website shortly. So I'm kind of spending some time doing reorganization of the website and adding content and working with Lindsay, Rowan, and other people to kind of add to that. So that's what I've been working on.
Excellent. Whenever you get a chance, would you mind just dropping the link for the Read the Docs site in the notes so that if people want to check out some of the work that you've been doing, they can do that?
Yep.
Excellent. Anybody else?
No, not on SimPEG.
Okay.
Well, why don't you give just like a quick update for everyone here? Because I don't know if John or Dieter know what you're up to.
Well, I've been working on and literally get lost a bit in creating some platform to explain what geophysics is to kids and the large public. And it's called GeoSci.xyz. And now we made the first video actually explaining just the word geophysics, with some street interview, asking people whether they know what geophysics is and stuff like that. And you can check it out. I can put the link to the blog in Slack.
Very great. Thanks, Sarah. Cool. And then one quick update from my end. If you were following along in the Python channel in Slack, there's a conversation that was going on there with mostly myself, Franklin, and Rowan, trying to figure out like what the data class should look like. And from that, I've sketched out an issue comment on like what some of my thoughts are. And so I'd appreciate if anyone wants to jump in and take a look and chime in. That would be great. And yeah, so sort of feedback in the next sort of day or two, and then we'll get cracking on an implementation. So
it's a funny name clash, sort of, because when I first read it, I thought you're talking about the new data class that comes in Python 3.6, 3.7.
Oh, okay.
But it's obviously the data class from SimPEG, another data class of Python. So yeah. Anyway.
Yes, thank you for the clarification. That is a good point. Cool. Okay. Well, if there are no other, John, was there anything you wanted to jump in on?
Oh, yeah, nothing right now. I'm just kind of working. Actually, I'm working on the Meg gradient stuff there. Just trying to get it running. So I should have actually some runs. I have my hands on some actual data, so I'm trying to invert it right now. So in about a week or so, I should actually have something to show. Excellent.
Cool. Okay. Well, I will turn the floor over to Dieter.
Hello. Yes. I think what I'm going to do is more show an example and then make it question and answer. I had the best intentions to create a presentation of some sort, but last week we were at Transform in France, and then yesterday came all our stuff, so it was kind of very busy. Yeah.
Yeah. How was Transform?
Good. Very exciting, very inspiring, very transformative. I don't know. I think there were about 26, and what surprised me the most is there were a lot from industry.
Okay.
So there are folks from Shell, Equinor, Dell, Schlumberger, DAG, Oxy. I think so. Maybe I forgot someone. But yeah, so there was a pretty broad range of companies present as well, next to all academia and so different sort. Agile Geoscience was there, of course. Yeah, I think that's it. But yeah, no, it was very good. It was very good. Very interesting. Exhausting. So, where should I start? Is everyone familiar with multigrid? Probably.
You might want to do like a
Like I never heard of it a year ago, or a year and 2 months ago. So for me, it was completely new. But the idea is basically that it's an iterative solver. So not unlike Paradiso, or what else do you use in SimPEG? In PyMath solver?
Mumps can be hooked up. That's also a direct solver, and then there's iterative solvers like conjugate gradient and things like that.
Yes. Yeah. Okay. And the basic idea is that you can go to smaller grids, so you keep the dimensions equally wide, but instead of having 24 cells, you just go down to 2 massive cells. You solve the system there, and then you upscale it and try to solve it there, and you jump between different levels of the grid. And the idea is to, on the lower grids, basically you capture the feature that are lower frequency of some sort, and then in the finer mesh you capture the parts that are from, like, say, higher frequency content. And the fact that you can do lots of stuff on lower grids means you can save a lot of energy and save a lot of memory, and also runtime. That's kind of the basic idea, I would say. But it's an iterative solver, so you jump through grid levels, and then the residual from you calculate left-hand side, right-hand side, and the residual is your new source term in the new grid.
Okay.
And then you solve for that bit, and then you always carry on the residual, right? Until this residual fulfills some criteria of tolerance or whatever.
And to go between grids,
Yeah.
is there like a physical property averaging that happens?
Yes.
Yeah.
So this method, which is based on Wim Mulder from 2006, he works at Shell and at TU Delft. He did this code, I guess, mainly for Shell. It was in this time, it was in MATLAB, and all the expensive functions were in C. Mesh files kind of wrapped C. It is some sort a simple implementation of multigrid in that you just combine 2 neighboring cells, and because you could create completely new meshes, right? But then the whole calculation would be much more complex. But it's just you combine neighboring cells and you average all physical properties basically inside those cells. So let's say your bigger cell has, in the 3-dimension, it has 8 cells, and then you just sum them up. Well, because you multiply them by volume in the equation, right? So it's kind of, to have them all, you sum them up, or you then split them up. So yeah.
So then over like a large cell that contains, say, 9 of these, it's a volume weighted average, but it's still isotropic, or do you get anisotropic, like an anisotropic representation on the coarse scale?
At the moment, you do it for each, let's say you have vertical or 2 horizontal and a vertical resistivity, you would do it for each separately with no interaction.
Okay, but if all of the cells are isotropic, but I have like the top layer is conductive, the middle layer is resistive, and the bottom layer is conductive, but each cell individually is isotropic, then when I average, I would still end up with something isotropic at the end of it? Okay.
Yeah. That's also the thing with if there is strong anisotropy or let's say strong variations, then the pure multigrid code can struggle. And so, but I probably show that better later. There are some modes where there are kind of two tricks. One is you only get cursor in some directions, and you're not getting cursor in for one cycle, and then you change that. So you can alleviate some of those problems. And the other thing is, instead of not coarsening, in between each step, we'll see that as well, you do smoothing, which is basically one or two Gauss-Seidel iterative solvers. So just 2 steps. So you just do some averaging, let's say. And you do that not for the whole problem at once, but you go from one node to another node. So you always just include all 8 neighboring cells. And one of the ways to address this problem with anisotropy is like, then you can do this smoothing in one direction completely at once. It means you slow it down a bit, you will need more memory, but you can get a better result in this. So yeah. I think for SimPEG users, the biggest difference is probably now you usually just define a solver, but you don't play a lot around with possible parameters, how to improve runtime for this particular solver, or how you can make it faster or use less memory. And then with the multigrid solver, you probably have to test a little bit how it will work fine. Yes, it's not just you can't throw everything at it like that and expect that it's much better. So you have to try different possibilities.
Okay.
Can I share the screen somehow?
Yes, it should be like if you mouse over the left, there should be a green screen share button.
Yes, the green. Let me see. But then let me bring over this windows here. Oh. Does that share my both screens? And that wouldn't be good.
Yes, I can see both screens. Or like I can see myself and then a background.
And let me try it here. And now? You still see both?
I still see the video and it looks like a notebook. Yeah, so I still see both.
Then if I just unplug it.
Right, now we see just the...
Okay, let's do it on the screen. So let me just run through a quick example, and then it's probably best you start asking questions, or I show you a few different things. So here I simply define a discretized mesh of what we have, 48 by 32 by 32 cells. Now, one of the things is because it always divides the dimension by half at each coarsening level. Cell meshes that are 2 to the power of n are best suited because you can coarse them down to all the way to 2. But you can also use in between, let's say 3 times 2, 2 times 2 type 2, or 5 times 2 times 2. But yeah, it should be a number. If you take a high prime number, then you can't coarsen it because you cannot divide all white cells by 2, right? This could probably be generalized, but it isn't. So yeah, just to keep in mind. And just a simple model, so 10 hertz here. This is an homogeneous model, so I just have here the resistivity in X is 1.5, the resistivity in Y 1.8, the resistivity in Z 3.3. And then I defined the source field. In this example where I did it compared it to SimPEG, we can all this define also just in SimPEG. So this is nothing, all this is nothing new, let's say.
Cool.
And then what is new is here now the solver. So I just quickly run it so you can see first what it means by multigrid. So we see here the original grid is 48 cells by 32 by 32. So, and the coarsest grid is 3 by 2 by 2. So we can coarsen it 4 times in each dimension, right? We can go from 48, it goes to 24, 12, 6, 3. And similar from 32, it goes to 8 to 16, 8, 4, 2. That's kind of the coarsening procedures. So we start off, the original model has almost 50,000 cells, but then the first problem we actually solve is just on 12 cells. Does that make sense?
Yeah, I think so.
So at the beginning here, I have a little QC plot. So, and this is kind of what you often see when you read up on multigrid. You have different plots that look like W's or V's or similar like this. So this is the coarsening procedure. So we go all the way down. And here on the bottom, we have a model from this 3 by 4 by 4 cells. We do smoothing here, which is 1 or 2 steps of the Gauss-Seidel iterative solver. And so it just do 2 iterations. So it will not solve it until it fits the tolerance. It just, how do you describe that best? It just has some iteration, so that's why it's called smoothing, right? It tries to adjust the parameters. But then instead of going all the way, it goes 1 level up. So then here we will have 6 by 4 by 4 cells, and it does smoothing again. And then it goes to the coarsest level again. And so like this, it just moves through the cycle and tries to solve here for the lowest frequency content, and then on higher level, it tries to fit higher and higher frequency content of your problem.
And so that trajectory, is that something that you defined a priori, or is that adaptive and it's figuring out like how many levels to go up and down as it's solving?
No, that is defined. This is sometimes you read it as full multigrid cycle. So you start with the coarsest and then go subsequently up and down. I think the original multigrid cycle is just a V cycle. So you go all the way down and go all the way up.
Mm-hmm.
But multigrid, in 1 cycle, you rarely solve it. So you see, in this case, I run 8 of those cycles. So this is just the first cycle, and then you do it again, and then you do it again, and you do it again. And another common, but the most expensive, is the W cycle, it's called. So you make little in between of each. It looks like a W, I guess. So you go to the lowest, you go 1 up, you go 2 up, but then again the lowest one, and then yeah, it's a symmetric cycle. But this one is very expensive because you see you need much more steps to solve. Telling that, I realize it's somehow difficult to explain. The thing is, multigrid can often be used for one of the solvers you're all familiar with, like big G-stab or conjugate gradient and all those, and can be used as a preconditioner.
Mm-hmm.
Right? And we can have a quick look at this. And we see here now, we actually run a big G-stab iterative solver. That's what is implemented in SimPEG 2, you told me, in PyMath solver.
Mm-hmm.
But just instead of running it straight away, we do multigrid cycles as preconditioning.
Cool.
And now you see it required 3 big G-stab cycle. If I take multigrid completely out, then probably 50 iterations, which I said to the maximum, is not enough to solve the problem. I would have to do many more big G-stabs. So multigrid can speed up other solvers quite significantly. That's another possibility, let's say.
And so right now, are you solving, this is implemented for frequency domain?
Yes.
Yeah. Okay.
Yes, that's one of the things. So it's implemented for frequency domain and just for electromagnetics with a source term, which sort of makes it just feasible right now for, yes, EM. I'm not even sure, because the magnetics is not explicitly involved. I mean, they are linked, so you could somehow get the magnetics field out of it. But right now it's just implemented for electric source, electric receiver. That's how by default it works.
Cool. And so, is it set up in like in the similar way to SimPEG, where like you're solving for the fields and then you interpolate those to the receiver locations, or do you have something different going on under the hood? Do you know what I'm saying?
Yes, how to get it out. Actually, at the moment, yes, I want to use the SimPEG thing, because at the moment I mostly just take the correct locations, which is the edges where the field is located at that moment. So I interpolate it like you do.
Okay.
But yeah, it's just, I mean, the whole discretized model is the same. So the calculation happens at the same point, so to say. And also how the source is defined, I think that's all the same as in SimPEG.
Cool.
Because did you have time to have a look at this one?
No, not yet.
So this is basically the one you sent me. I can quick go through this. So these are just the parameters we define. You probably sent them to me with conductivities, but yeah, it's pretty. Then we send the mesh. You had there a nice, you calculated there within the cell the source term, and I have there a little routine in my code, but it's basically the same. It takes the cell or the cells where the source is located, and if you would average them, it will sum to 1, right?
Yep.
Then the mesh, and then this is how you usually, yeah, this is the model. I think you defined that model. So it's just here, air, C, there's a little target in the middle, and the rest is an homogeneous background. And then let's jump the multi-grid code and go here. So you define the PDE, the receiver locations, all the source survey, you pair them, and then you run it, which in this case took 4 minutes. It's actually not too long, so let's run it. So in this notebook, I do everything the same. The only difference is then I call that solver with the model and the source field, and you do call dpred. Is that correct?
Yes. Yeah.
Yes, but that is basically the only
difference. That's really cool.
Difference. So I think we should somehow be possible to integrate it more. I'm not exactly sure how. Because, well, it would be nice to have it somehow more integrated into PyMath solver, because then we could probably just run inversions with it.
Yeah.
But then I'm not sure how that works, because it's only working for EM right now, so it wouldn't work for all the other. So we probably have to put in some checks there. And also the main difference, as I said earlier, is that the solver has to know about the physics, because each level it calculates the field, right?
Yeah.
Which is very different from Paradiso or the other solvers. So I'm not sure how to go about that, but I think it should be possible.
And sort of how much does the solver need to know about the physics, I guess? And so maybe what I'm getting at, and this will be more evident, I guess, when I have a chance to dive into the code and when others do too. But like how how entangled, I guess, is the physics with the solve?
I guess at two levels. One is the coarsening and the prolongation. There you just have to make sure that all the properties you need are getting coarsened or prolonged, as they usually call it. So made one level down, or one interpolated, or summed up, right?
Mm-hmm.
This is one point. This is more about the physical properties, which is kind of more mesh related, I guess. And then the solver needs to know, specifically in the smoothing steps, it does calculate the whole. It does solve the whole equation.
Okay.
So it has to know basically everything. Let me see. Maybe in the. So this is all the same. You have the E grid with the dual grid, which is kind of the interpolated cell. Yeah, I don't think it's getting clear just from quickly. You see, when you go down,
Mm-hmm.
you have here these little V's, right? Or new one, new course, new two. And this is called the pre-smoothing. Then the smoothing on the coarsest level, which is kind of a solver. And then you have the post-smoothing. So in all these, you do iterative solutions to your problem, and all these need to know, well, it's always the same function, but this function needs to know your problem. Does that make sense?
Yeah, yeah.
Just this one. So you solve this at each smoothing step, and yeah.
Okay.
So maybe we have to set up once a meeting. Also, I don't know, did you work with PyMath Solver, or was it all done by Rowan?
I've dug into it a bit. Most of it was written by Rowan, but like at a conceptual level. And I've dug into the implementation too, so I'm happy to chat through that. It seems like this might. It's not clear entirely like where it would sit. It might integrate better to be imported from SimPEG, just because it needs to know so much about the.
Yeah, that could be. Mm-hmm.
But that said, like there might be some things that we can do to abstract like which physics it's solving, because we store models so similarly across all of the different physics implementations. Like basically sort of
Right.
whatever you need to like whatever you need to prolong should be relatively straightforward. Yeah, but this is like we can dive into the implementations a bit more offline, I guess.
Yeah.
Are there other questions? I want to make sure I'm not the only one talking. If there's other people have questions.
Sharing screens. Let me quick stop that so everybody's visible. You are sharing screen. Stop sharing.
Oh, that's really promising. That's really cool. Like the small example you showed, like the difference in like speed and conversions is massive. So yeah, I haven't really dived into Python yet.
Oh, Kevin, we're getting a large. I think, Dieter, you're okay. I think that was Kevin. Kevin, I've just muted you. Feel free to unmute if you have a question.
Yeah, so no, like would be great to see that more integrated with SimPEG.
And Dieter, is there a way to, so if you're solving the frequency domain problem, is it still parallelizable over frequency? Like, is each frequency independent, or do you need to be solving them in any specific order?
No, but what is my next topic is to make some wrappers to do time domain, but still calculated in the frequency domain. But we have some ideas how we can probably bring the frequencies down to 20 for a big 3D model to have all time domain solutions. But then you can start with one frequency, and then this result you can give as input to the next frequency, so it doesn't start with 0 or with nothing. So it can go as usually the result changes smoothly over frequencies. You can give in the output from one to the next one, but then you're kind of forced serial, or you could just run them in parallel at the same time. That they are not. It's free in this respect. Yeah.
Cool.
But yeah, that's the thing is adding new methods. I think it would be possible. It's not on my list, but I would be very happy to, or at least discuss where we should have to dig in. My points, the next points are time domain and general anisotropy. At the moment, it's triaxial anisotropic. So I want to see how difficult it would be to extend that, because that's part of the to-dos of the project. So I should focus on those. And time domain too. So yeah.
Cool. And have you thought at all about the magnetotelluric problem? Would incorporating boundary conditions, would that be possible? Or one approach would be thinking of it like a primary secondary, but I don't know if that's like set up or if that's in scope.
Primary secondary, that definitely would work. Yes. Because I also know they tested that in the original code, so that definitely should work. Boundary condition, that's actually an interesting thing, because you in SimPEG you also just push out error, right?
You cut out
let's say.
So in SimPEG right now, I believe that the main implementation is primary secondary. We can go in and change the boundary conditions. I think that's only working for a single implementation, like a single PDE at the moment. But that's something we could play around with if that's of interest to you.
Yeah. Yeah, because we were thinking if maybe the perfectly matching layers would be a good thing for the air boundary, but we have never invested time so far. Because we need quite a lot on ourselves. Sorry, yeah.
I was going to say, if you wanted a few ideas for different ways to solve the problem, the E3D MT, so like a GIF, like Fortran code, the theory for that is actually online. And so there has been some time spent to go think about implementation of 1D and 3D boundary conditions. And so, yeah, I could share the URL for that. So the theory section is, yeah, been reviewed by Roman Sheckman, who works with our group. So that might be a place to look if you guys were thinking of trying out some different things.
Yep. Yeah, that'd be great. I could change.
Just like a question, just for general interest, but like this multi-queen methods, like, so right now you do that on a tensor mesh, and you divide the mesh by 2 everywhere. How would that work, for example, on a node tree where you only refine in your area of interest? Instead of refining everywhere, you do that on a node tree and you refine only a certain area. Would that be possible?
Yeah. I think that shouldn't be too difficult, because you wouldn't have to change all the smoothing stuff. You would just have to change or adapt the functions to the.
Sorry,
Yeah.
Can you give that a try again, Dieter? I just muted Thibaut. We were getting feedback. You might not have heard that, but that was coming through everywhere else. Sorry, Dieter.
Wow. So I repeat, me.
Yeah, if you don't mind.
Yeah, I think it shouldn't be too difficult, because most of the internal parts wouldn't change. It's just for the tree mesh, we would have to extend it on how it's coarsening and refining the grid, basically. And so we would have to look into tree meshes, how this is done, so it sort of keeps track. Because now at some point, like in Python, it's very easy. You just do the semicolon, semicolon 2. And so it takes every second node and you have a coarser grid, right? So in the tree mesh, this would have to be a bit more sophisticated, but I don't think it would be too difficult.
Okay, nice. So that would be only, like the only change would be to change the refine function instead of dividing by 2, using something more advanced. Okay, that's cool.
Probably. There might also be, like, at the moment, the iterative solver, it's probably one of the reasons also why it doesn't use so many memories. It's just solving for one node with its adjacent 8 cells and then moving through the whole 3D cube, right? And this will probably also change if you have a tree mesh, because you wouldn't have a regular mesh to go through. It would probably depend, yeah, how a tree mesh is set up. I'm not sure about that.
It actually should be very natural for the tree mesh, because basically how we think about creating and storing the tree mesh is, like, conceptually, it just starts from a single cell, and then we just progressively refine. And so actually the entire refinement structure is basically like how the tree mesh is stored. So all you basically would have to do is you walk up that tree,
Yes.
up and down. So that should be like a pretty natural extension if that's something you want to play around with. Like,
so you could loop over, just to say, over X. Or
you wouldn't necessarily loop over X, but we can loop over, like, refinement levels of the mesh, if that makes sense. You sort of have to do everything at once, because you can't just, like, walk right across X, because it's not a tensor grid. Like, you can't just delineate what's going on in only the X direction and sort of ignore the rest of the dimensionality of the mesh.
right.
Yeah, but we can walk the grid in a fairly, like, we can walk it by levels of refinement. And so if you need to coarsen by a factor of 2, like, that mesh is very easy to fetch. Oh, did everyone just drop off? Hello?